One day, a business user complains that the report page is taking too long to fetch the result. This was not the case earlier. So what has gone wrong? Snowflake claims that it is a lightning fast data warehouse system. Is that all fake? And when you hear this, do you ever think of Snowflake's micro partition might be playing a role here or something else? Maybe or may not be. So the question is, do you need to know about Snowflake's micro partition concept to create a partition? The answer is no, straight no. Then why should you worry about it? Well, as a smart data engineer like you must know how micro partition play a crucial role when it comes to really large data set. By knowing how it works, you will be able to analyze how many partition your table has, the concept of total partition versus scanned partition, the effectiveness of query pruning, clustering depth and clustering overlap concept, performance degradation over time, reclustering, and many more. The flow and natural arrival of your data and the DML operation have impact on your query performance, and this video will deep dive on all those concepts. So stay tuned until the end of this video to get the answer of all those questions. Welcome back to my channel Data Engineering Simplified and to this real jumpstart course for Snowflake data professionals. The last 12 episodes in this series already covered from history to architecture, bulk continuous data load, unique features to multi-cluster virtual warehouses, and many more important concepts. This episode, the episode 13th, will primarily focus on micro-partition concept and how it has to be used to design the cluster key for your large table, or to investigate why a query is taking so long and how to use clustering histogram to understand the key distribution. We will practice everything using Snowflake free trial edition and go through all the concepts covered in this course. Many of you really like this tree map approach as it keeps us focused without wasting any time. So let's review it quickly. We'll first start with partition versus micro-partition and try to understand what is micro-partition in Snowflake. What is the benefit of micro-partitions within Snowflake and how the micro-partition impact the query performance in Snowflake. Then we will see what all metadata is managed by the cloud services for the micro-partition. We will also understand the data clustering concept in Snowflake. We'll see how the SQL looks like when it comes to creating a micro-partition or alter or dropping it. How we can see the micro-partition for a table or a set of tables. What is the limitation when it comes to the external table and micro-partition. Then we will also understand quickly how the auto clustering works and fact about auto clustering and the cost of auto clustering. We'll get into the performance evaluation where we'll understand how the query pruning or the data file scanning can be validated via query profile concept. Finally, we'll cover the clustering depth and clustering overlap and understand through few examples. We will also see how the data profiling looks in Snowsight modern web UI. It is not very different and it does not show any different value. It's only the layout in Snowsight is slightly different than the legacy web UI. So we are going to cover all those 4 major sections under the Snowflake partition and clustering. So let's start. Before we proceed further, I have a small announcement to make. If you really want to master Snowflake Cloud Data Warehouse, I would recommend you to look into my channel's playlist. The playlist section includes SnowPro and Advanced Certification Guide, mock question series, important SQL functions, Snowflake connector series, Snowflake features and limitations, and many more real-life hands-on videos. By watching my free video series, many data engineers, leads, and architects, and even managers are getting certified in SnowPro Core and Advanced Certification. And the success rate is very high. I'm not lying. Just look into the comment. You don't need to buy any expensive courses. Just subscribe to my channel and I guarantee that you would easily learn this technology and get certified in just few weeks. So one small favor, if you are learning from my channel and my content, please hit the like button and this gesture will make me super happy. Let's understand the history of partition. We have different kind of partition technique and they help us to optimize our IO operation and focus only on specific data blocks rather reading entire data set. If you have to read the entire data set, for example, gigabytes or terabytes of data to serve a single query with a specific filter criteria, then the query performance will suffer due to full data scan. and the partition strategy comes to rescue by chunking the data based on different partition technique as shown above. In this example, a cell's data is chunked by list partition where partition is applied based on a distinct region. On the other side, the range partition where number of partition depends on range of values of particular partition keys. In this example, Jan to Feb, March to April and May to June. And on the other side, hash partition. This technique distributes the data in more uniform way under various partition block. There are some other techniques and they are used for different purposes. Sometimes it is very hard to decide. If you have worked on Apache Hive, you have partition as well as bucketing concept, and sometimes it goes very complex as well as confusing and adds extra burden to design data storage using partition techniques. In large data project, data arrives on different frequencies and based on partition rule, it gets appended under different physical location within the disk. On the other side, analytics workload read the dataset continuously. For a large or a very large dataset, partition help us to narrow down to scan a specific physical file and serve the query. The database or a data warehouse engine must have a brain to decide which physical block to read so it can reduce the IO operation and hence reduce the data transfer cost. Snowflake Micro Partition works. When you load data into Snowflake, it goes via stage process and generally we don't onboard data via single insert statement into Snowflake, and we have seen this in earlier chapter. The cloud service layer, which is also called the brain of Snowflake, analyzes the data chunk, convert into columnar style, compress it and create a proprietary data format called micro partition and make it available for analytics workload. When different workload access the data, the cloud service layer, which is again called the brain of Snowflake, knows everything about this partition or micro partition like minimum values, maximum values, range values for each column, unique values for each column and additional attribute, and accordingly it creates a physical plan to read the data and serve the query in more optimal way. These micro partitions are immutable files, means every new data arrival creates a new partition or new micro partition. As per Snowflake documentation, each micro partition size varies from 50 MB to 500 MB. Since it is a proprietary data format, end user don't have access to it. They are immutable, encrypted, compressed and columnar format. Snowflake micro partitions are not very static in nature. They are very dynamic in nature. Snowflake cloud service layer decide how the micro partitions would be created and it varies from 50 MB to 500 MB as shown in this diagram. Understand the micro partition conceptual model with a very simple data set. We can call it customer table. This 20 records and the customer domain is taken to demonstrate how it works in a more visual form. Let's say we have customer table with 6 fields having numeric, text, boolean and date data types. When the data is loaded first time via stage and the copy operation, the cloud service layer analyzes the data, identify the cluster key automatically by scanning the data, chunk the data in smaller batches, convert it into columnar format, compress it, encrypt it and create micro partition out of it. The size of micro partition ranges from 50 MB to 500 MB based on the nature of data, which includes data type, data cardinality and many more other attributes. The cloud service layer has all the details like number of rows, min and max, distinct values and other attributes for each partition. So you can see that after partitioning, the row number 4, 8, 13 and 19 from the left side are part of one of the micro partition. And if you run a query with a date of birth less than 1998, Snowflake has to read only one micro partition if I consider this sample dataset. Likewise, other micro partitions are also created and Snowflake Cloud Service does everything for the developer. You don't need to specify anything as long as you have tables having dataset less than terabytes. It would be hard to find what is the size of each partition as Snowflake does not provide any visibility about it. It is possible the second partition might be smaller or bigger, and in this example, the second partition has row number 5 to 8, which is actually different position in the source file. If the micropartition size is big, then it may have more rows as shown above. If you pause for a few seconds, and you can see Snowflake has ordered the data based on date of birth, converted into columnar format, compressed it and creates a smaller chunk as micropartition. So it can save cost and also less IO operation and more cost effective. And you don't need to know anything about clustering, compression, encryption, etc. So you don't have any design overhead, and Snowflake makes your life super easy for most of your use cases where you have gigabytes of data. Unless otherwise it's a multi-terabyte of data, you really don't need to use any clustering concept in Snowflake, and it is done automatically for you. The next question we can have, the how many micropartition does Snowflake create? The answer is thousands or millions for a very large table. If we take the same customer table example and assume that it has terabytes of data, then Snowflake may or will create thousands or millions of micropartitions. For every new arrival of data chunk, it does not modify the old micropartitions as they are all immutable, and hence it adds more and more micropartition as new data arrives. Does CDC or delta file arrival change existing micropartitions? Micropartitions are immutable, and once it is created, it never changes. So let's say we have this large customer table having terabytes of data and also eligible for CDC processing. The Snowflake Cloud Service has already created thousands of micropartition as per its initial data load. Now we have two delta files with handful of record. In your case, it could range from few hundred to thousands of record. These data files are not only consist of new records but also consist of update on existing dataset, and your use case may have a deletion too. Now, when CDC1 and CDC2 arrives at Snowflake, the cloud service layer again analyzes the dataset, understand existing partition or cluster key, chunk it as necessary as per your copy command and convert it into a columnar format, compress it, encrypt it, and then create new micropartition. In this simple example, we have just taken 4 records, record number 4 and 5, record number 12 and 13, and we see that there are some changes has happened. In this example, since we have a handful of record, it may create maybe one extra partition. However, in your case, it may create one, many or many thousand. It all depends on the dataset, and this overall process is very proprietary to Snowflake. So our next question is, too many micropartition degrade query performance? Maybe yes, but not necessarily. Use cases like time series data where you have only append operation and large chunk of data is arriving, then thousands or even millions of micropartition is not a problem. However, if you have a table where many DML operations like individual inserts or updates or deletes are happening, the new partitions are created as old micropartitions are completely immutable. And hence, your query may slow down or you would observe performance degradation. String depth and clustering overlap. We will go back to our customer table, which has a field ID, first name, last name, date of birth, active flag, and city. For a simplicity, we are just considering 20 rows. When we fed this data to Snowflake, assume Snowflake has clustered the data using date of birth field, and primarily for a safety purpose, we can assume that it is considering year within the data field. As we have seen in our earlier example, it has created 5 micropartition. We know Snowflake keeps the metadata information for each micropartition file, the min and max value for the date of birth. If we execute query where date of birth year is 1995, then it can easily check how many partition it has to read, and it will read only micropartition 1, which is P1 in this example. When we apply filter criteria for year 1997, it has to read 2 micropartition as year 1997 is there in micropartition 1 as well as in micropartition 2. The max of micropartition 1 with respect to year is 1997, and the min of micropartition 2 is also 1997. Since it has to read 2 micropartition, we can safely say that 1997 is having one overlap and the depth of the cluster key is 2. Now let's change the filter criteria to value 2003 and analyze the pattern. By looking at the min and max value for the year, we can safely say that the Snowflake has to read 4 micropartition file P2, P3, P4 and P5, and here the overlap is 3 and the depth is 4 because the year 2003 has to be available in one micropartition. However, this micropartition cluster key is overlapping with other 3 micropartitions, and that's why the overlap value is 3. However, the depth is a 4. This is a very simple representation, and for a large table, it would be hard to visualize this way. So Snowflake shows this detail via histogram, and we'll see in the later slide. Now let me represent this data set in a different format where I am keeping partition files from P1 from partition 1 to partition 5 on x-axis and the cluster key, which is date of birth in this case, in x-axis, and ordering them from min value to the max value. And if they share a cluster key, in this case I am considering the year value from min or a max that define the overlapping. And you clearly see in this example, the partition 1 and partition 2 share 1997, partition 2 and partition 3 share 2003, partition 3 and partition 4 share 2003, and partition 4 and partition 5 share 2003 again. So if I expand my table further to add a frequency marker with min value and start looking downward in the rows, for year 1995, the depth is 1 as it is available only in partition 1, partition file 1, and it has 0 overlap as it doesn't overlap with any other partition. When I consider the year 1997, it has 2 depth and overlapping with one other micro partition. So I can safely assume that it has 1 overlap. The year 2003 has 4 depth and overlapping with 3 other micro partitions. The year 2008 having no overlap and having a depth value 1. So as per this calculation, the average depth for the table with respect to year in the date of birth field is 1.6. I have taken a very simple example for the demonstration, and instead of considering date of birth as a full field value, I considered year so I can easily visualize and represent in a pictorial format. Now let me help you with a real life example from Snowflake table, how its information schema shows the histogram for a cluster key within a table, and we will see it later in this episode by having a hands-on exercise. When I fire a query on the system function called cluster information by giving the table name and the partition key, the result shows the total number of partition is 875, and the calculation we have seen in the previous slide gives 3.69 as average depth, and they both are matching. So you can also pause the screen, perform this calculation. So this is how the Snowflake calculates the average depth using cluster information and shows it via histogram. So let's quickly go through the micropartition summary and its benefit. Unlike traditional static partitioning, Snowflake micropartitions are derived automatically. They don't need to be explicitly defined upfront or maintained by user. As the name suggests, micropartitions are small in size, 50 MB to 500 MB before compression, which enables extremely efficient DML and fine-grained pruning for faster queries. Micropartitions can overlap in their range of values, which combined with their uniformly small size helps prevent skew. Columns are stored independently with micropartition, often referred to as columnar storage. This enables efficient scanning of individual columns. Only the columns referred by a query are scanned. Columns are also compressed individually within micropartitions. Snowflake automatically determines the most efficient compression algorithm for the columns in each micropartition. These are the very important points, and if you are appearing SnowPro exam, you would get at least 3 to 4 questions from this summary. So please pause it, go through them, and if you have specific questions, put those questions in the comment section. Let's start with our hands-on exercise. Create a table called order table and creates 3 instances of it. The order table has order key, order date, and other order related columns. The order key and the order date are the natural field. If you don't specify any cluster key or a partition key, Snowflake will use its own brain to partition the table. So for the first table, we are not specifying any cluster key and relying on Snowflake to apply it automatically. The second table instance is a cluster by order date, which is the most suitable field in this table for partition. And the third table is created with order priority, and there are just 5 different priorities in this table, and hence the cardinality is very low, which is a wrong selection of the cluster key. All the tables are populated with 5 million rows at one go. The total size of the data is around 3.5 GB for all the table. All the tables are having the same data set with exact row count. Here I am in my Snowflake free trial edition, and first let me change the context via SQL statement. Let's create the first table called T1 underscore no cluster key, and this table does not have any cluster key. You see, my SQL constructs are just a simple DDL statement. My first table is created. I am having the table T2 underscore order underscore DT, and this is having a cluster by order date. Now I am creating a third table called T3 underscore order underscore priority, and this table is cluster by the order priority. So I have created all the table. Now let me populate data, and here I am fast forwarding it, as populating 5 million record in each table takes some time. So we can see all the 3 tables have got the data, and it has exactly 500 million rows, and the total size of the data is 12.9 GB. Now let's see the table and associated cluster key. So for that I will run show tables followed by a like statement. So I can see. So here my T1 with no cluster key, it has 500 million rows. I have T2 with order date as a cluster key, which also has a 5 million rows, and the cluster key and the cluster by is order date. And on third table we have a T3 order priority, which is cluster by order priority. Here I can see this automatic clustering is off, and for other two the automatic clustering is on. Since I have defined the cluster key, it will automatically cluster as and when the new micro partitions are created, and Snowflake will realize that the micro partition for this table is not working as expected, and it will start an auto partitioning automatically. However, for the table 1 where we have not created a cluster, it has not enabled the automatic clustering. So when you have a large table and if you feel that your query performance has degraded, you can add a clustering key and it will automatically enable the automatic clustering flag. Now let me run the select count query and see how much time does it take. This doesn't take much time because this data is coming from your cloud services. T2 is 5 million rows and T3 also 5 million rows. Now we would like to run a query against each table and see the behavior. We will use the timestamp as a field so it does not use the cache. You can also disable the cache using the parameter setting at session level or account level. To understand the behavior appropriately and the time taken by it, we would use a different warehouses. But before that, I would like to run the first query and see if the order priority equals to medium with current timestamp greater than this works for 10 records or not. So it has worked properly because I just populated data. In this step 7, we will choose a different virtual warehouse, and I have already created for this demo. And I'm going to choose the virtual warehouse called WH01, and I'm going to run the first query once again as we have run it here. And I just want to make sure that the warehouse is running. We don't wait for warehouse to come up. Though it is a small warehouse, it takes no time to come up. Let me validate. Yeah, so I am using WH01. I would run this select star from T1 no cluster with following where clause. So it 924 millisecond. Okay. Now I'm going to step 8. I'm going to run exactly the same query. However, this time I would run this query on T2 table by changing my warehouse. I can see that my warehouse is running. Now let me this select query. I got the result in 920 millisecond. Now on the step 9, I would choose a warehouse 3 and run the select query on table 3. So I am on warehouse 3. So here it took 982 millisecond. Okay. Now I would go and see how the history tab looks like with respect to overall performance. So when I look into the query history tab and I see the table 1 select statement has taken 924 millisecond and it has read 305 megabyte of data. On the other side, the table 2, which has the order date as a cluster key explicitly defined, took 920 millisecond, but it has scanned 449 megabytes of data. The table 3, which has a order priority as a cluster key, has taken 982 millisecond and read 528 megabyte of data. So if your tables are having gigabytes or even terabytes of data, if you do not specify the cluster key, the Snowflake is intelligent enough to identify the cluster key automatically and you don't have to worry about it. And this is what it shows. Now let's jump into the alter statement, which you can apply for the cluster key on a table. So if I have to change my cluster key, how would I do that? For T3 order priority table, we had selected the order priority as a cluster key. And now if I have to change my cluster key from order priority to the order date, this is how this statement looks like. You have to say alter table followed by table name and you will give the cluster by clause. So let me run this and see how does it work. And the statement executed successfully. If I have to verify that, I would use show tables command. And here I can see both the tables are having order date as a cluster key. If I have to drop a cluster key, I will again apply the alter table and I would say drop my cluster key. And here in the line number 12, I'm going to execute this SQL. Now my cluster key is dropped. Let me validate this. And I can see my cluster key is dropped. Now we have seen in our initial conceptual diagram that if I have a lot of DML operation happening on the table, then I would prefer to do the recluster, and the recluster is kind of a deprecated now in Snowflake, and Snowflake allows the reclustering happening automatically. But what if I run this statement? It end up with error saying that unsupported feature now. Now Snowflake also allows you to enable or disable the recluster. Now let's try it out. If you have a cluster key and wants to disable automatic reclustering, then you again have to alter the table. And let me try this suspend recluster and resume recluster SQL statement. So it says my auto clustering has been suspended, and let me validate this by using a show table command. Here I can see my automatic clustering is off. Let me re-enable the reclustering. Let's see the table again. And my reclustering is on. So this is how you can enable and disable the reclustering. Can I enable the recluster on a table which does not have a cluster key? And let's try that out. So this is the table T1 underscore no underscore cluster, which doesn't have any cluster key. And I would like to enable the reclustering, and let's see how this SQL behave. So it says that it doesn't have a cluster, and that's why you cannot do the reclustering on this table. So important note, automatic clustering consumes Snowflake credit, but does not require you to provide a virtual warehouse. Instead, Snowflake internally manages and achieve efficient resource utilization for reclustering the table. So this is how your alter statement with cluster key on a table works. So the next question is that, can we have cluster key for an external table? And let's try it out. So this is a simple external table which I am creating using my location, my state chapter 13, and I am making the auto refresh false and attaching a file format. Here on line number 26, I would like to use currency as my cluster key, and let me run this SQL statement. There is a SQL compilation error because the cluster by is not supported for external table. So external table doesn't support cluster key and it supports only the partition key, and we have seen this in earlier episode. You can follow the link above. Now I have got some complex queries which has a lot of join, filter criteria, and it is accessing a lot of large table like order, sales, customer demographic, date dimension, item, promotion. I ran these queries, and since it took time, I'm not going to rerun them. I will directly jump into the query profile page and we will understand how this query profile look like and how you can see the clustering detail by looking into the query profile screen. So here I can see I executed queries on a 2x large warehouse and it read quite a lot of data, and let me click on one of them. So this is how it looks like. When I click on the profile, it loads the profile screen, and here in the profile screen on the right pan you can see it has taken 1 minute 3 seconds to process the entire query, out of which 21% is a processing time. And if you look into the pruning part, which is most important when we talk about cluster key, it has read 88k micro partition out of 200k total partition. So this is how you can understand that how many partitions have been read for your query, and you can optimize or retune your query or change your partition column as per your use case. If I come to the middle pan, here you can see what is my different scan, and for that scan how much partition has been read. Out of 32k micro partition, only 13k micro partition has been used. If I click onto the other table, here out of 86k micro partition, 33k micro partition have been used. If I go to this another table, it has read almost all partition. So this is how the partition is playing a very important role. So by looking at this screen, you would know a lot about clustering keys and how the micro partitions are being used during the query, and you can analyze by looking into this node diagram and build your understanding. When I go to this Snow site, I can go to the compute and the history tab, and from here I can click on this query ID. It shows the very similar screen, and I can click on this table scan, and here I can see exactly the partition scanned versus total partition, how much data has been sent, how much data has been read. This screen shows a similar information as we have seen in our legacy web UI. Move to our next section, where we'll try to understand some of the system function provided by Snowflake to understand the clustering depth as well as clustering overlap. So this is our first system function, which is called clustering depth, which takes only one input and it takes the name of the table. So we have already set the context, and now I'm going to run this select statement which calls this clustering depth system function. Since T1 no cluster has no cluster key, it returns that this doesn't have a cluster key. The T2 table has a cluster key order date, and let's run and see what is the result. So this brings your cluster depth as 3.6903, and we have seen how the cluster depth and cluster overlap is calculated in our earlier slides. Now T3 also has a cluster key. However, during this practice we dropped it. It also returns that it doesn't have any cluster depth. So T3 order priority is not cluster. So this is how this function works. What is the cluster depth? And by that way, you can make a conscious decision whether you have to apply a recluster or you have to change the cluster key. Let's go to another function called cluster ratio. Now cluster ratio is currently deprecated. The cluster ratio is a function which takes the name of the table followed by the cluster key, and then it returns a value. However, this has been deprecated by the Snowflake. Let me run it for you. So it says that unsupported feature cluster ratio. So let's go to our function called cluster information. So cluster information is another system function which takes name of the table followed by the name of the cluster key or any other field from the table. In this case, I am considering the T2 order date table, and I am passing the order date as the second parameter, and let's see what does it bring. This return a JSON value which says that my cluster key is order date. It has a total partition count 875, total constant partition count is 38, average overlap is 4.8, and average depth is 3.6. We have seen how the average overlap and how the average depth is created in earlier slide. Now this partition depth histogram, so it shows that there are 31 micro partition files which does not overlap. There are 2 keys which are available in 59 micro partition. There are 3 keys which are available in 325 partition. There are 4 keys which are available in 265 partition, and so on. And by considering this frequency and this number, you actually calculate your average overlaps. So if you stay on this range where overlap is less, your performance for the query would be better. As you go down in this number and there are more and more overlaps or more and more micro partition overlapping with 16 or 15 or 32 or 64 keys, it means that your distribution of keys are across many micro partition, and to read a certain filter criteria it has to read so many micro partition. So you need to make sure that this histogram is more concentrated towards number 1, 2, 3 and not at the tail side of the histogram. If more and more DML operations are happening on the table, you may constantly see that this histogram values are changing, and by looking at or by analyzing this histogram pattern, you need to make sure that recluster is executed appropriately or you enable the automatic recluster in this. So I hope this summary and live walkthrough of micro partition has been a meaningful session for you. I know it was a bit confusing to understand, and if you practice them on a regular basis, you would be able to understand better. Now it is time to jump into a very exciting feature of Snowflake called time travel. How this time travel really works in Snowflake, cost anything extra? If so, how much? And many more about this unique feature. If you are curious about it, watch the next chapter, chapter 14, and learn everything about time travel.